Let's continue our analysis of the common emitter amplifier, the Class A amplifier. So we were looking at the AC operation. So we're going to consider what happens when we modify the base current. And at first, we're going to look at the operation with no load. Okay, this is the easiest to understand. And we have some numbers here. Let's imagine that we have a quiescent current through the collector of 6.8 milliamps, which gives me a voltage across this 1 kilo ohm resistor of 6.8 volts. I'm going to assume a VCE voltage. Now, this is just given to you. You don't figure this out. You can just take the data down. VCE voltage of 5.2 volts. And we're going to have the emitter resistor holding a 3-volt drop. I do not care what the value of my emitter resistor is right now because I'm looking at the AC operation, and this capacitor takes that emitter resistor out of the circuit. As you can see, all of the variations in the current are going to go straight to the capacitor. So now, let's analyze this simply. We're going to rise in base current. That's going to pull more collector current. Okay, let's imagine that we actually have a rise that takes me to 0 voltage at the collector to emitter. So that means that I'm left with, we said 0 voltage, but I have to say that I'm going to have the minimum saturation voltage at the collector emitter. That would be 0.2 volts. So I have basically dropped 5 volts across the collector and emitter. I'm going to rise 5 volts at the collector resistor then. Okay, so that's going to take me, let's look at the node voltages. Before anything changed, this node voltage was at 8.2 volts. That's the 5.2 plus the 3. Now I have 6.8 volts across the collector. That's a total of 15. I'm going to go down to my 0.2 volts, which means I have fallen, if you were to look at an oscilloscope here, I have fallen 5 volts. Okay. Now I'm going to continue to change my base current. I'm going to go back down. My base current is going to now go to 0, which is my quiescent point. I'm back at 8.2 volts. That's right here, 8.2 volts. And I'm going to drop my base current so that I am choking the collector current. I'm decreasing my collector current. That's going to decrease my voltage across the collector resistor. Okay, you see the decrease right here, which increases the voltage across VCE. Remember that RE's voltage is being supplied by this capacitor. It's doing the smoothing effect. It's adding, it's discharging and recharging based on the variations it feels. So here we have the 0 condition, and now we're going to drop our base current so that we're choking this collector current. What happens here now? Your voltage here rises by how much? How much can it possibly rise? Well, if I drop all of the current to 0, that's 6.8 volts that has nowhere to go except this collector here. So this is going to rise above 8.2 by 6.8 volts. That's a value of 15 volts. That's VCC. Okay, the node voltage here is going to be equivalent to VCC. because there's no current through this collector resistor anymore. But remember, there is current down here. So we have a total jump of 6.8 volts. So please notice my rise and my fall at the oscilloscope end here is going to seem like it's 5 down and 6.8 up. This capacitor won't let the oscilloscope see the average 8.2 volts. It's going to isolate it from that DC voltage and is only going to pass through the AC alternation with a 5 volt downward peak and a 6.8 volt upward peak. The reason why it is uneven is because VCE and the voltage across the collector are not equal. So you have different amount of room on both ends. Okay, we're looking at the extreme conditions. If we were to completely turn off the current and the collector, and if we were to drop the voltage down to its floor across the transistor. Now we're going to think about this again, adding a load. So now we've added our 1 kilo ohm resistor as a load. And we're going to try to mirror the same circumstances we had with no load. See how things change. So in this situation here, when we had no load, we were increasing the base current, and that dropped my transistor's voltage to the floor. It was a 5 volt drop because my floor was 0.2 volts above our ease voltage. Okay, so my floor was 3.2 volts. Right, remember that this was here 3.2 volts. And this middle line here, remember, is 8.2 volts. Okay, so now if I do the same thing, and basically the drop in 5 volts translated into 5 milliamps more of current. We have to keep that in mind that this is a current controlled device. I'll repeat that. This is a current controlled device. So what's happened really is that IB is pushing 5 milliamps more of current in. I don't want you to associate it with the voltages so much as IB is demanding 5 more milliamps. Okay, so before without a load, that 5 milliamps translated into 5 volts more at RC, that brought us to the floor, so we couldn't really do any more. Now I have a load resistor. And that load resistor is going to respond to AC changes because the capacitor will allow that current to flow. The request for more current is an AC request, right? So it's going to pull from this resistor here. We're actually going to have 2 streams of current. And that means that the requirement for 5 milliamps will be satisfied in half of the time. So by the time the voltage across the collector emitter has dropped just halfway to 2.5 volts, it's already drawn all of the current that is required by the additional base current. Remember, we have to think about what the base current is asking for. We're assuming that it wants only 5 milliamps more. So 2.5 volts is sufficient to get that additional 5 milliamps from both the resistors, collector resistor and load resistor. So remember, we have the picture of the 2 of them in parallel when it comes to the AC model. Now we see how they're acting in parallel. They are actually 2 branches that are feeding in to the transistor. That's kind of cool when we can see things that are on a schematic in real life, in real physics, we can see it. Okay, so now let's do the reverse. We've just gone down only to 2.5 volts. We've squeezed the bottom of this waveform, instead of going all the way down to 5, we've gone down to 2.5. Now, what about the other side when the base current drops? So in the first scenario, I dropped 6.8 milliamps. Basically, I cut off that whole ICQ current, 6.8 milliamps. Now, we're going to see what happens if you drop that same 6.8 milliamps. The key to understanding this is realizing that when you are stopping current, you are raising the voltage barrier where the current would have entered. So in the same way, when we want to draw current, we drop the voltage barrier, we lower our voltage to create a sink. In this case, we're going to push back against the voltage by increasing the voltage level at the collector of the transistor, right here where the 8.2 is. So we're going to rise above 8.2. Now, in the no load situation, we went all the way up to VCC. We rose to 15 volts. That stopped all the current through the collector resistor. If we did that again now, if the transistor rose by 6.8 volts, we would have a total of 15 volts across the capacitor and the load. Now, the capacitor was sitting at 8.2 volts. Rising above will force current through the capacitor, and this is an AC current. So it's going to create a current through the load. Where's that current coming from? Because we have stopped the current from the collector resistor, and the transistor does not transmit current in the opposite direction. It's like a diode in that sense. So there's a contradiction here, an inconsistency. Here's what's going on. The transistor's voltage does rise, but it only rises halfway, about 3.4 volts. Because at that point, the collector's current would be diverted to the load. So rising 3.4 volts shuts off the current in the transistor and diverts the rest of the current through the load. Now, that might have seemed like a little bit of magic to you, so we're going to make it something that you could actually figure out on your own. So we're saying that our down peak here, our low peak is only halfway, and we could see that because we did some simple math, and we saw that at half the voltage, I'd have the full current, the 5 milliamps that I had before, I'd have the full current. Now on this side, on the upward swing of the voltage, which is suppressing the collector current, we're going to only need to rise up to the point that stops 6.8 milliamps of current. Okay, that's how much current we had suppressed. This is the ICQ current. We want to suppress all of that. So with the load, we're going to see that at a rise of about 3.4 volts, we will have half of the current stopped here and half of the current stopped here. Remember that in the parallel configuration, the current is always being split according to the resistors RC and RL values, right? If it was a different ratio, if it wasn't 1-to-1, we could still determine the ratio of the currents using our current divider formula. There's nothing more than parallel resistors. So we would use that value, the voltage value that would cut off 6.8 milliamps from both branches. Now, it seems that we're reducing our peaks. We have just squashed our gain. And in fact, if you look at the AC model, our gain is proportional to RC in parallel with RL. It's a very simple formula. We have defined something called the AC emitter resistance, little re. I'm going to define it here. That is simply equal to capital RE, okay, over the voltage across that, you'll see what that is in a minute, times 25 millivolts. This comes from some physics about solid state, the solid state material. We don't need to know the derivation of that, but we can accept that as something handy for us. So this can also be written as 25 millivolts divided by the current flowing through the emitter. That's the DC current. Remember that there is no AC current flowing through our emitter right now because we have that capacitor. So there's something to note about this. This is going to tell me that our gain, which eventually we'll come up with, is going to be related to that capital RE value. Even though it's not in the AC model, it does affect things. Well, let's finish our discussion here. So we see we're coming up with our gain formula here. We see that Vin is going to be equal to the current flowing through the collector times this emitter AC resistance. This is simply something that we accept, as the physicists have worked hard on coming up with this, so we're going to work with it. Okay, and let me clean this up a little bit. This picture, let's clean this up. So we have our transistor here. This is our AC model. Clean that up. And so there is what we call an AC emitter resistance across here. And this is the input voltage. That's the AC input voltage. So we also are going to look at the KCL of this circuit and say that the current flowing through the collector has to equal that current flowing through RE. We're going to assume that the base current is negligible. So now we can make a very important simplification. We're going to write the output voltage. Okay, hope you have those notes. Let's erase that. The output voltage in terms of RC and RL. You could do this yourself. So V out. Okay, first we're going to write just a simple Ohm's law. Remember, V out is the collector to emitter voltage. It's that voltage there. And according to Ohm's law, it's also going to give us the current. V out over the parallel combination of RC and RL is got to be equivalent to IC. Okay, it's clear in this picture. And if you study this circuit here, the original circuit, you can convince yourself of that as well. You can. So now we are going to do some algebra. V out is equal to IC times this parallel equivalent resistance. And in the textbooks, they like to call that little RC. The little RC includes the load. So little RC, okay, and that is going to be divided by Vn, which we have the equation for above. That's just IC times this effective resistance at the emitter. Cancel out the ICs, and you see that my gain, this is now my voltage gain, is equal to the ratio of these parallel resistors, which is the RC right there, divided by the emitter resistance, the AC emitter resistance. This is great news. We have such a simple formula that we can use to figure out the gain of any common emitter circuit. Let's clean this up really quick so you can write this properly in your notes. So RC, this is our final formula. There's a lot more than we can say about these things, and we will in class, but right now I'd like you to work on playing with the numbers, looking at multisim, and seeing if you can verify the concepts that we just talked about. So there is one final point that we will make, and it's an important one. Notice that we squashed the sinusoid at the output when we added the load. That's an important result, because what it means is that, remember this floor we had of 5 volts because we couldn't get below the 0.2 volts here. We couldn't get below 3.2. Well, we're not anywhere near 3.2 now. We're at 2.5 when we did the same thing we did before. So that means that when I've added the load, I actually have more room on the bottom to go down. You know, this corresponds to an increase in current, which means I can actually get more current than what I previously had, the 6.8 milliamps. I can actually reach a higher current than what my DC load line would tell me I could. That's interesting. So that's the first point. You need to know that in the AC mode, you actually have exceeded the limits that were put on you by the DC circuit. This maximum current was VCC over RC. And with RE in there, you would actually make it over RC plus RE. That is no longer a constraint when you have the additional load providing current to you. Now, and just to be clear, it's not the load that provides the current. It's not a battery. It's the AC source that is providing current through the load. The load is actually able to be a conduit for current from the AC source. Okay, so now what about on the top end? If I could go lower or have more current in my AC model, can I exceed the top where I had VCC before? Can I somehow get higher than that? Well, right now, this level here is not VCC. It's about halfway up to VCC. So it's more like, let's see, 11, it's 3.4 plus 8.2. Okay, so we would have, okay, 11.6 volts there. Now, what does that mean to me? Can I actually, and this is the situation where we were pushing back on the current. The voltage is rising, which is stopping the collector current. And at that point, all the collector current has been diverted to the load. There's nothing going down my transistor. Okay. Is there any way to get higher current? Higher voltage? Can I push past that 11.6 volts? Well, if I did, I would basically be trying to get more current to flow through the load, right? Because it'd be a higher voltage, which means that I want more. Higher voltage here means it's across the load here. So I want to get more current through the load. Well, right now, that current through the load is coming from the collector and VCC. And it's matching because there's no other current path. They have to be equal. If I try to push more current through, that current would have to come up from the bottom here through my transistor into the load. And the one thing the transistor won't do is give you negative current. It won't transmit current in the opposite direction. We've said that before. So that's an impossible situation. So unfortunately, although I have some more current available to me on the bottom end here, that's a nice perk. I can't get more voltage. I actually am restricted on the top end below VCC. So my AC circuit will not allow me to reach VCC at the peak. So if you were to look at the new load line, adjusted, here's my DC load line. And it stops at VCC at the bottom. Okay, remember, this is the voltage across the emitter and collector of the transistor. It can't get higher than VCC, and it can't, the current through that section to the collector can't rise above the saturation current that I calculated before with just RC and RE. But now I'm actually going to rise above that saturation current because I'm allowing this this AC circuit to take me higher. I'm using its power, and I actually have to go below VCC because once this is zeroed out, there's nothing more I can do. I can't go below the zero current point here, right? If I want to raise this voltage even higher, that means I have more voltage I'm trying to push through, more current I'm trying to push through the load, and there's no source for that. So our peak is going to be limited to this new value, okay, VC max, which is related to the mix of RC and RL. It is directly related to their ratios. Okay. In class, we can do example problems where we can solve for these values, but it's just important that you understand the concepts that I'm presenting here qualitatively. And that's all she wrote. Thank you.